All right, so let's talk about when we use logs. We've talked about exponents, and exponents kind of make sense. Um, when you're going to multiply something, but like for example, when we're doubling something over and over and over again, that's when we're talking about exponents. Now, when would we use logs, especially this log base 10 that keeps popping up? Like there's even a button for it on the calculator. When do we use this log in real life? Well, we actually use it a few times more than we think whenever you hear the Richter scale, whenever you hear like, oh, that was like a 3.5 earthquake, so it wasn't that bad and things like that. That's when we're using logs. So what the Richter scale is it tells us how strong an earthquake is by base 10. So for example, if a regular earthquake is so much and we have something like, oh, that was like a um 4 on the Richter scale, we're not just talking about what are we measuring there. It's like, well, 4 is like a lot bigger um than a 3, and that is actually 10 times bigger, because what we're actually measuring when we do a Richter scale is we're measuring to the power of 10 is our base to the power of 4. So it would be 4 times greater than what's known as this A amplitude for a detectable one that actually does measure on the Richter scale. So the Richter scale, if you guys don't know, is this little machine that goes back and forth, and it moves based on vibrations in the earth. So if we can detect it, meaning this thing will wiggle even just a little bit, that's a detectable one. So we measure it based off of what can actually be measured with this tool. So if it's a 1 on the Richter scale, that means it's 10 times bigger. So it's going to be 10 times bigger than a one that we can barely feel, that this machine right here can barely sense. So that's why the power of 10's used a lot, because it's easier to think of things as like it's 1,000 times bigger, it's 1,000,000 times bigger, because we can just use log base 10. If we use log base 10 of 1,000,000, that's just going to pop out a 6, because it's 10 times itself 6 different times. Base 10 is actually really useful to use, because if we're doing something times itself, we just count the zeros. It's the easiest way to think of base 10. So whenever you see something log base 10, you know it's like, and you pop out a number, you're like, oh, wow, that's a 3.5. That means you know it's more than, so if it's 3.5, the example I gave, so it's log of whatever, log base 10 of whatever, and we get like a 3.5, you know it is at least 1,000 times bigger. So that's kind of a way we can use these logs in a useful way, is Richter scale. Another one is decibels. Now decibels, we usually measure times 10. The reason for this is since sound is so tiny, like the weakest sound we can hear is and the actual sounds we can hear. So basically, the range of human hearing is really small. So um, if we were to measure something, we're gonna get like little decimals. Like let's say the smallest sound we could hear would be like, I don't know, a 2, and we have another number that's like a 2.01 or something. I'm just making these numbers up. But you would get this really small decimal um, by power of 10. So yeah, you are getting a power of 10, but it's a power of 10 that's like a decimal bigger. So what we do is we have to multiply it by 10, so it actually like looks like actual numbers that we can use. Another time that we use this besides using it with large numbers with the Richter scale, or a small window of hearing with decibels, is pH. We're talking about millions and billions of little hydrogen atoms that determine how acidic something is. So this is when we can use these formulas. So these formulas will pop up again. So I do recommend writing these down. I might even have to come back to this slide to do it. So that's why you hear me talking about it a lot. It's like, oh, I really need to cover this in case I have to come back to it. So looking at this, a Richter scale model, for example, it's going to have the same things, the same key features of a function. So everything's going to kind of be the same. We have it's an increasing function. It's negative. Negative values are little fractions, a very small part of the graph, but x's can never be negative. Y values can be negative because there's little fractions. We're talking about x1. So these negative values are just used to kind of deal with fractions because the negative values are exponents. Remember that whatever we're getting from a log is essentially an exponent value. And the intercept, so most of it's going to be the same. There's not going to be much difference. Now, when we're talking about the decibel model, what's happening here is we are multiplying this by a factor of 10. So that's why you see that these numbers are a lot bigger. We're dealing with like by the hundreds. So you we do have that intercept there at 1. You can see that our asymptote's the same. I don't think they measure, do they? They don't even mention the intercept here. But I believe the intercept would technically be 10 because we're multiplying it by 10. But you wouldn't be able to see it because we're talking about numbers so big that there's only a small window where you would see that x-intercept is 10. So what happens is we would get the log, whatever this is, something over, what variable do they use? Variable negative 10 to the 12th, and whatever we're talking about here. And because we would get a 1 from here, we would eventually multiply that 1 by 10. So what ends up happening is our x is 10 and our intercept is 0 because that's where the intercept is. So it still has the same properties as being multiplied by 10. And as you can see here, there's very little change over all these decibels that we talk about. All right, so pH. So pH has a negative factor to it. It's been a minute, so literally you're going to see me go back, just like I mentioned. I haven't taken chemistry in a while, so the less amount of hold on, measurement of hydrogen ion levels, the pH measures the acidity of alkaline. So what's happening here is because of this negative, we're talking about so tiny amounts of hydrogen atoms, like I believe we're talking about molar concentration of hydrogen atoms, independent variables. I want to say that they do it in moles. They do it in these numbers that involve a lot of atoms per a small amount of area. So they do the opposite because if you have more hydrogen ions, it's more acidic. So by putting the negative in there, we're talking about actual hydrogen that's in there. We're measuring the inverse of the hydrogen. So if it's a small number, it actually means there's a lot of hydrogen in there. Larger number means the opposite. So that negative allows us to kind of graph this. So, but because there's a negative, we end up having to flip our our graph here. So that negative in front of the formula flips our graph on the x-axis. Everything else is going to be the same other than the fact that now we're decreasing. So as we decrease from there to there. Um, what's happening here is essentially we've stopped measuring at 14 because it grows so slow after 14 that you might as well just say 14's our cap. So again, it's just the graphs going basic. I'm very sorry. My chemistry knowledge and my geology knowledge, as well as my physics knowledge, is all limited. So Richter scale being about geology and decibels being about physics and chemistry. Uh, More of a math person. I can explain the math. So let's get into an actual math problem. So I'm back in my element. All right. So we're looking at this activity here. So Janet works at an IT company. Her boss asked her to create a program that randomly generates a password of length L. So L is how many characters are in this password. Each character in the password is selected from X possible symbols. The symbols include uppercase and lowercase, so that's at least uh, 52 because we have 26 letters in the alphabet, lowercase and uppercase, and in the alphabet, and 10 digits, so 0 to 9. We have 10 digits. There are no fractions, decimal values. So they're just integers, basically. Uh, to check the strength of the password, Janet created the logarithmic function. So she's going off base 2, log base 2. Therefore, increasing either L or X will strengthen the generated password. So if there's more of a possibility of letters instead of it just being 62, believe I did the math on that right. Instead of there being 62 possibilities, that's maximum. If we were to lower that to, let's say, we don't want uppercase letters, that cuts it almost in half. Um, it's going to be a weaker password versus, like, let's say we start introducing other symbols. So if we start introducing other symbols, that's going to increase our X. Also, making the password longer also makes it more viable, more safer. So here's the graph with 7. So she's dealing with a 7 character password right now. There's 7 or not symbols, letters or numbers here. All right, so let's look at what we could answer from here. So when we're looking at this, we're going to ask ourselves, what's the asymptote? Well, we can see it very obviously here that the asymptote is still x equals 0. So I'm going to grab, it says it at x equals, I'm going to put 0. The intercept here, normally, like I said, it would normally be 1, but I believe in this case it's 7, if I'm not mistaken. And just to double check it, because I'm starting to have doubts on myself, I'm going to open up Desmos. So this is a good way for you guys to check yourselves on your answers. So I'm going to graph this. Oops, I accidentally opened the scientific calculator. Useful tool, but not what I wanted at the time. So let's take a look here. So we're doing log base 2. Unfortunately, Desmos has their keyboard in a very bad spot for me. Let me see if I can. Nope. Desmos, why? Actually, I could get upset at Screencastify for this one. Give me a second here. I know there's a way to do. I don't want to get rid of my tools though. This is really well. I can get rid of it and put it back on. So you want to go into here, go into functions, miscellaneous, I believe is where all the logs are. I don't think it's trig. Statistics, no. Histogram, no, that's distribution. There it is. It's in miscellaneous log. We're going to do base 2. I was debating on doing the log base 10 of whatever we're talking about. over log base 10 of 2, but I think this works. We have the tool. And in case you guys need visual aid for that, let me put my tools back up. Come on, Screencastify. I need my tools back on. Options. Where are my tools? Oh, wow. Well, I guess I'm going to use a different tool to write on the board because I can't figure out how to write. So I was going to do this log, oh my gosh, log of x over log 2 times 7. This is the same thing as what I'm about to do right now. The only difference is, obviously, this one you can enter into calculators. This one, some calculators have it, other ones don't. And just to prove that it is the same, I'm going to do this right now. I didn't want to have the, oh, actually, the 7 on top works. Log of x, and then log base 2. You can see it's the exact same thing, just a matter of how you write it. Okay, so let's take a look. Oops. No. Oh, yeah, I actually do want that. All right, so if I look here, oh, I was wrong. It's still 7. Oh, because you're multiplying it. Okay. So what's happening is the log would be different. So forgive me on that other one. So this is still the x-intercept is 1. Technically, that's incorrect. It should be 1 comma 0, but I digress. What's our domain? Our domain is all of our xi's that work. Remember, we can't have negative numbers, so we're going to start at 0. Technically, we start right after 0. That's why it's a parentheses. And behavior. So as we go to the right, x approaches infinity. But as we go to the left, x approaches negative infinity. So it's this one. If we go to the left, it's not going up, it's going down. So as we're going to the left, our function's going down. All right, and this is always going to be increasing. Our graph is increasing here. All right. So this 7 does not change the asymptote. I think I talked about that earlier. In a previous video, it doesn't change the asymptote. It just kind of amplifies how it grows without changing it. So my apologies for mentioning that on the other one with the Richter scale. It wasn't correct. Which statements are true? So we have to think about this logically. The password is weakest if it uses a single symbol for all seven. Yes, of course. What this is saying here is this is saying that if x is equal to 1, yeah, that's probably going to be pretty weak there, right? Next one, the strength of a password increases with a decrease in the number of symbols. That's not true. We just talked about this. If we increase the number of symbols, we're probably going to get better. So instead of, so for having an L, we want that, or actually number of symbols, that's X. So if we increase the number of symbols, the strength of the password gets stronger, but we're not going to decrease it. The stronger, so we're not going to do this one for sure. We want to increase the number of symbols, not decrease them. Next one, the password is stronger with an increase in the number of symbols. Yeah, that's the exact opposite of what I just crossed out. So we definitely want that with a single symbol for all 7. Yeah, it's probably the weakest. We can't really have a fraction. The password is strongest if a single symbol is used for all characters. Isn't that what they just said over here? Oh, strongest. Nope. Nope, nope. That's the exact opposite. I read that wrong. There are two possible symbol options per character to produce a password with strength 7 bits. There are 7 symbol options per character to produce option with 7 bits. Okay, so that's what the 7 is. I don't think it mentioned it in the story when I was reading it. But I'm assuming that it's 2 because we're doing log base 2. So yeah, it's 2 because we're doing log base 2. I don't know why this keeps asking me about deleting it. That's new. So that's how we would kind of talk about this. This one I know I kind of glossed over really fast, but it's just the idea that um, what our base is. There's two possible options, uppercase or lowercase. And with the numbers, we're also talking about the symbols on top of it. So evaluate it, kind of think of what you're doing. So if I were doing this, I would tell myself, I definitely have trouble with the x-intercept. I totally forgot that the number in front of this does not change my intercept. So if you get this wrong, definitely be careful with that. Um, and don't just, you know, take the answer and run with it. Reflect on why you got it wrong. Seeing the answer here that's provided for you is definitely there to help you kind of understand what's going on later. All right, so moving on to another one. This thing always takes a while to load for me. So, actually, where are we? Let me see. No, keep going. I was thinking like this might be a good spot for me to leave off, but let me keep going. So now we're talking about piecewise function. So the idea of a piecewise function is it kind of changes its shape halfway through or something. There's certain parameters that cause something to change. And this happens all the time. Um, for example, let's say you're paying in a parking lot. You're parking in a parking lot. So you park your car and they are always charging you and charging you. But then at a certain point, they're like, oh, you reached the maximum number after a certain thing. We're never going to charge you more than that. This happens a lot with book fees and things like that. Or let's say, like, well, if you use something, um, from 0 to 4 hours. Like, let's say, I don't know, you're renting computer time. At 0 to 4 hours, it's, I don't know, $2 an hour. I'm just making numbers up in this random scenario. But anywhere from 5 to 10 hours, we're only going to charge you $1 for that hour. You've been using it a lot. You're obviously a good customer. We're going to give you a discount after a certain amount of time. So that creates this linear function from 0 to 4, and then a different linear function with a less steeper slope um, for the rest. So remember, slope is rise over run. All right. So let's get cracking with these uh, functions. So, for example, this one, I don't know what's happening here, but we see here from anything less than 1 is this function right here. It has a slope of 1 and an intercept of 3. You can see that right here with the mx plus b formula. But then something happens from 1 to 0, and we start getting a negative slope here. And it starts going down. And all of a sudden, after 2 and on forever, this infinity symbol says forever, it goes on this way. So this is a piecewise function. It changes based on a certain time period. So when we deal with piecewise functions, it's kind of important to kind of figure out what we're talking about here. So from here, anything smaller than -1 is this linear function, and then anywhere from -1 to +1, there's no change. There's no slope. It's going to stay at 1. And then all of a sudden, after 1, it starts growing parabolically, I guess would be the word. It's a quadratic function. It starts growing. All right. So moving on from there, we see that there's another function. So this is so piecewise functions are basically they have different equations that work for different things. This is measuring for example, we're talking about g of x. This function g measures the same thing, but it changes based off of the certain time, certain input. So all we know is that x is an input. It's our independent variable, and y is dependent on that. So this changes based off the time period. And we're going to talk a little bit about these characteristics, about when does it increase, when does it decrease, when does it start, when does it stop. These are all key features of the function. So for example, the key features of this is that it starts at -5 and ends at -3. Then there's a period where nothing's happening. There's nothing in between this -3 and 2. And if we get really specific, see how there's no equal sign? This never touches -3. That's why it's an open circle. And it never touches 2 either. So stuff's happening there. So there's things we can talk about there, things we can write in. So that'll be the premise for where we start off. Our next video, I'm sorry, I know I said I would have these out earlier. These videos just take a really long time to record, and I apologize for that. But I do have some time set aside today to record it. Um, so I will try to help you guys out with this. I know this is a lot of material to cover. So hopefully these videos are helping. Please let me know, guys, how I can help. All right. Have a good one.